Okay, in this video, we're going to go through the next section in the Rust programming language book. This section is on data types. So let's just jump right in. Every value in Rust is of a certain data type, which tells Rust what kind of data is being specified so it knows how to work with that data. A little bit metaphorical, it's like what really is doing the knowing. The language itself is just a language. I assume this is to say, you know, the parser, the compiler, all that jazz, the lexer. I'm not exactly sure where all that stuff comes in, but, you know, I don't think it's the syntax itself. The syntax is how we say it. We'll look at two types of data, scalar and compound. Keep in mind that Rust is statically typed, which means that it must know the types of all variables at compile time. That's true, and that is, I guess, the downside, in at least a downside of static typing, is that you have to say a bunch of things up front correctly. There's not really any kind of promiscuity of types during the runtime the way that there is about types in Python, where you can really substantially change the types during the runtime because everything is behind the scenes kind of generic, kind of that you don't need to say what it is because it'll handle whatever it happens to be as a general Python object or as special cases of it. So the compiler can usually infer what type we want to use based on the value and how we use it. Yeah, I know we've seen that so far in Rustlings. I can't remember if we've seen that in the Rust programming language book yet, but certainly I expect it'll come up. In cases when many types are possible, such as when we converted a string to a numerical type using parse, as we saw in the comparing the guess to the secret number section in chapter 2, that was the programming a guessing game chapter, we must add a type annotation like this. Let guess, specified to be U32, be starting with a 42 that is not a number but is actually a string literal, and calling parse on it, and then expect. So the parse part is looking to the U32 to know what the type needs to be, and if you run into an error in the result, then it's going to print not a number or display not a number and then exit out of the program, or you get the successful result, an OK result, the OK variant of the result type, result enum, and you just can grab that out and use it for whatever purposes. Okay, so if we don't add the U32 type annotation shown in the preceding code, Rust will display the following error, which means the compiler needs more information from us to know which type we want to use. So if we used cargo build, we would get this error compiling no type annotation, let guess, equal all that stuff except for the type annotation. And then the type must be known at this point is what the error is telling us from the compiler, and that it cannot satisfy this abstract trait thing. And we'll get into traits later, but this from stir error. Help give, consider giving guess an explicit type, like let guess, and then fill the type in here, just like that U32, and then the rest of it. Okay, so you'll see different type annotations for other data types as we go along. Next thing, scalar types. Scalar types represent a single value. Rust has 4 primary scalar types: integers, floating point numbers, booleans, and characters. You may recognize these from other programming languages. Let's jump into how they work in Rust. Certainly if you're coming from languages like C, that should be very familiar. Python's a little bit different, where we don't have chars per se. We have strings. Rust also has strings, but Rust is a little bit more similar to C in that there is not that many layers down. You really are dealing with arrays, or in Rust, vectors of chars. But similar idea. Rust does have string types, but they are compound. So let's move on to integer types here. An integer is a number without a fractional component. We used one integer type in chapter 2, the U32 type. This type declaration indicates that the value is associated with should be an unsigned integer. Signed integer types start with I instead of U. This takes up 32 bits of space either way. Table 3-1 shows the built-in integer types in Rust. We can use any of these variants to declare the type of an integer. Now, fractional component might sound like a completely informal term, and maybe it is intended there, But there is this like fractional part function in mathematics that literally is what it sounds like. It's the fractional part, so it only goes up as high as 1, because past that, the fractional part of the number just becomes the next number up. So fractional part can be defined as this piecewise function of evaluated at some value x is x minus the floor round of x when x is greater than or equal to 0, and otherwise it's equal to the ceiling round. Okay, that's just a little bit of mathematical preamble, and if you go through this wiki page, you'll find that there are other ways to represent it as well. Great. So we've got this table which has the length, whether it's signed or not, and the unsigned version. So not whether it's signed or not, but just showing the signed version and the unsigned version for that length. So for 8 bits, it's I8, and for unsigned, it's U8. For 16 bits, it's I16. Unsigned, it's U16. 32 bits, it's I32. Unsigned, it's U32, and so forth until you get to 128 bits. And then there's also this arc, which is, I believe, short for architecture, although I think we'll get into this, which also has a signed and unsigned version of it that has to do with the number of bits to keep track of. So it's usually used for things, by the way, of like the length of an array, such things like that. So each variant can be either signed or unsigned and has an explicit size. Signed and unsigned refer to whether it's possible for the number to be negative. In other words, whether the number needs to have a sign with it signed, or whether it only ever needs, or whether it's basically always positive and can therefore be represented without a sign, so unsigned. It's like writing numbers on paper. When the sign matters, a number is shown with a plus or minus sign. However, when it's safe to assume the number is positive, it's shown with no sign. Signed numbers are stored with the 2's complement representation. We can read a little bit of the Wikipedia, but we don't want to dwell on this. So 2's complement is the most common method of representing signed, positive, negative, and 0 integers on computers, and more generally fixed point binary values. 2's complement uses the binary digit with the greatest value as the sign to indicate whether the binary number is positive or negative. When the most significant bit is 1, the number is signed as negative, and when the most significant bit is 0, the number is signed as positive. That's probably enough there. Basically, it's a sequence of bits, and we're using the first bit on the left of that sequence to decide whether it's a positive or negative value. Okay, so each signed variant can store numbers from minus 2 to the power of n minus 1 all the way up until 2 to the power of n minus 1 minus 1, inclusive, where n is the number of bits that variant uses. So an I32 can store numbers from minus 2 to the power of 7 all the way up till 2 to the power of 7, then minus 1, which equals minus 128 all the way up to 127. So you can see that it's not really symmetric about 0, which is one of the little gotchas you need to watch out for with the sizes. Unsigned variants can store numbers from 0 to 2 to the power of n minus 1. So a U8 can store numbers from 0 to 2 to the power of 8 minus 1, which equals 0 to 255. Those who are familiar with certain representations of pixel color channels will recognize 255. So additionally, the I-size and U-size types depend on the architecture of your computer program, the architecture of the computer your program is running on, which is denoted in the table as arc. 64 bits if you're on a 64-bit architecture, and 32 bits if you're on a 32-bit architecture. You can write integer literals in any of the forms shown in table 3-2. Note that number literals that can be multiple numerical types allow a type suffix, such as 57U8, to designate the type. Number literals can also use underscore as a visual separator to make the number easier to read, such as 1_000 for 1,000, which will have the same value as if you had just written 1000, 1,000. So literals, integer literals in Rust. You got number literals and examples here. Here's a decimal one where we've got 98,222. You got hexadecimal where you've got this 0xFF. an octal representation of 0077, a binary representation 0b, 4 bits that are ones, and then another following 4 bits that are zeros, and then bytes, which are for U8 only, where I can write a shorthand of B, and then what looks like basically it's like a char of A. So how do you know which type of integer to use? If you're unsure, Rust's defaults are generally good places to start. Integer types default to I32. Now, I guess one of the things when it's not that you're not sure about what you would do, but what you're unsure about for users, that there's a thing I think we'll cover later in this book called generics, where you can write it in a more general way that accepts different types, and so you don't have to either write out implementations for every combination of types, which is quite a lot, or to force it down to a very narrow type, like just picking only float 64 and nothing else. So the primary situation in which you would use iSize or usize is when indexing some sort of collection. Fair enough. I'm sure we'll see examples of that later. So integer overflow. This is kind of a little box where we're going to get into a smaller piece of context here. Let's say you have a variable of type U8 that can hold values between 0 and 255. Sure. If you try to change the variable to a value outside of that range, such as 256, integer overflow will occur, which can result in one of two behaviors. Okay? One, you're compiling in debug mode. Rust includes checks for integer overflow that cause your program to panic at runtime if this behavior occurs. This seems like pretty desirable behavior, especially for development where something should just simply break so that you know that it's broken. Now, Rust uses the term panicking when a program exits with an error. We'll discuss panics in more depth in the Unrecoverable Errors with Panic Bang section in Chapter 9. Sure. When you're compiling in release mode with the -- release flag, Rust does not include checks for integer overflow that cause panics. Okay. Instead, if overflow occurs, Rust performs 2's complement wrapping. In short, values greater than the maximum value in the type can hold wraparound to the minimum of the values the type can hold. In the case of a U8, the value 256 becomes 0, the value of 257 becomes 1, and so on. The program won't panic, but the variable will have a value that probably isn't what you were expecting to have. Relying on integer overflow wrapping behavior is considered an error. Yeah, I feel like I would rather be explicit and make sure that things are correct up front than rely on an implicit behavior of whether you're in debug mode or not. For debug versus release mode, I mean, I very much think that I want optimizations to occur, but this seems to me to be something that substantively changes behavior beyond just being faster. So I feel like trying to be correct and explicit up front is preferable here. To explicitly handle the possibility of overflow, you can use these families of methods provided by the standard library for primitive numeric types. So here's the first bullet: wrap in all modes with the wrapping _star methods, such as wrapping add. Okay, could do that. Return the none value if there is overflow with the checked _star methods. Return the value and Boolean indicating whether there was an overflow with the overflow _ methods, and saturate the value's minimum or maximum values with the saturating _star methods. I imagine that this will probably come up again if it's an important thing, but I think the thing to do here as a matter of good practice is to just simply avoid relying on this kind of implicit behavior. So the explicit handling of the possibility of overflow, these seem like good options once you become familiar with them. Floating point types. Okay, so we've moved on from integers onto floats. Rust has two primitive types for floating point numbers, which are numbers with decimal points. Rust floating point types are F32 and F64, which are 32 bits and 64 bits in size, respectively. The default type is as F64 because on modern CPUs, it's roughly the same speed as F32, but is capable of more precision. Interesting. I actually wonder what the difference is. Maybe for extremely, extremely high-performance stuff that doesn't have to be as precise, like extremely high speed level of performance, and you're willing to be less accurate, less precise, maybe both, that maybe F32 is still preferable. I don't know. So all floating point types are signed. Okay, fair enough. Here's an example that shows the floating point numbers in action. So, okay, let's actually make this our first file. And let's go cargo new and call this floating point types. Let's go in there and let's open up an RS file. So let's say let x, and here we're not explicitly binding the type, but we're going to say is assigned or bound to the value of 2.0. And they're saying here that de facto, this is an F64, a float 64. Whereas if I say let y, F32 explicitly is equal to 3.0, or is bound to the value of 3.0, I should say, then this is explicitly assigned as an F32, and that's what it will be committed to be. So I should be able to just get that and get some warnings because we didn't actually use the variables for anything. The Rust compiler is always looking for dead code that maybe you should actually get rid of. But anyway, this is a small technically correct program, sorry. Okay. Let's move on to numerical operations. So, Rust supports the basic mathematical operations that you would expect for all the number types: addition, subtraction, multiplication, division, and remainder. Integer division truncates towards 0 to the nearest integer. And that's important to keep in mind if you're looking for like rounding behavior, and that you may want something like nearest integer rounding, or you might want floor rounding or other kinds of things that you may not want to always rely on integer division as a way of rounding. It will round towards 0 to the nearest integer, not nearest integer in general or other things. So the following code shows you how you'd use each numerical operation in a let statement. Let's do it. What should we call this? Let's call this cargo new numeric operations. And let's jump into the source main here. And we'll go, first of all, addition. And for addition, we could say let sum. Now this one hurts my brain a little bit because, frankly, I am used to Python where the word sum is actually a reserved keyword, so you wouldn't do this in Python, calling something a sum explicitly. Just hurts my brain a little bit, you know? But as far as I know, this is fine in Rust. It's technically fine in Python, but you're overriding built-ins, which I'm not a huge fan of. Okay, let difference 95.5 minus 4.3. There it is. We're getting some unused variable warnings from the compiler, but that's okay. Let's get a multiplication example. Let product equal 4 asterisk 30 is our 4 times 30. For ordinary floating point division, we got, let's say, let quotient is equal to 56.7 divided by 32.2. And let's get truncated assigned. Here we've got integer in the numerator, integer in the denominator, and this should give us a result. Results in -1. Sure. And then finally, we will do a remainder function example using just the remainder operation, no function per se. 43 modulus 5. And we get warnings, but that's technically fine. Okay, so that's what that looks like in Rust. Each expression in these statements uses a mathematical operator and evaluates to a single value, which is then bound to a variable. Appendix B contains a list of all operators that Rust provides. We probably don't need to do that right now, but maybe, oops, maybe we should just quickly do some print line macros. So you can put some there. I'll just print the 1 for now. just to show something in the output there. Okay, there's our 15, 5 plus 10, 15. Great. All right, the Boolean type. As in most other programming languages, a Boolean type in Rust has two possible values, true and false. Booleans are 1 byte in size. The Boolean type in Rust is specified using bool, the bool keyword. For example, if I've got, let's do it again. Let's go through this in an example. So let's go cargo new, I don't know, the Boolean type. Let's say let t is bound to the value true, and let f, which is then specified with type bool, be bound to the value false. And I think the point they're making here is that you could be implicit, as in the first case here, or you could be explicit, as in the second case. Yeah, okay. The main way to use the Boolean values is through conditionals, such as if expressions. We'll cover how if expressions work in Rust in the control flow section. Now, this is a subtle point that you may have missed if you're coming from Python, is it says if expressions. It doesn't say if statements. In Rust especially, they're careful about this distinction between statements, which do have semantic value, and expressions, which have semantic value, but they also are evaluated. They become a value. They're not just an instruction. So that's one thing that I think we'll probably see later. I won't go into it further detail now, but it's just food for thought that you can actually have an if statement become a value. An if expression become a value that you might use somewhere. Okay, so the value type, or the character type. Rust's char type or char type is the language's most primitive alphabetic type. Here are some examples of declaring chars. Cargo new, the character type. Should we say chars or chars? I've definitely heard people from the C language world call them chars, but it's kind of closer to how we say the word to say cars, isn't it? I think so. Okay, so let's see. Be bound to this string literal z, or char, I should say. The difference there is the double versus single quotes there. We could also be explicit about the type by saying char. There's no way that I'm going to spend time looking up this mathematical symbol in Unicode for the integer, so we're just going to copy paste that one right in. I try to type a lot of the examples, but I don't think we're going to do it for that. Okay, with explicit type annotation. I just realized it's actually raining pretty loudly outside. Hopefully it's not too bad for you folks. Explicit type annotation, sure. And then the last one here was let heart-eyed cat be bound to the value of the little heart-eyed cat emoji. It's so cute. Okay. Just double check I don't have any typos here. Really, if I'm trying to check only for the sake of checking, I could go cargo check. Okay. So what's next for us? Now that we specify char or char literals with single quotes as opposed to string quotes, note that we do that, which use double quotes. Yeah, okay. Rust's char type is 4 bytes in size and represents a Unicode scalar value, which means it can represent a lot more than just ASCII. That's true. If I remember right, Unicode's like a strict superset, right? There are definitely characters in Unicode that don't exist in ASCII, but I think basically all ASCII codes are in Unicode. So, accented letters, Chinese, Japanese, Korean letters, emoji, and zero width spaces are all valid char values in Rust. Also math symbols, as we saw up here. However, a character isn't really a concept in Unicode, so your human intuition for what a character is may not match up with what a character is in Rust. Oh yes, this has to do with the... What is this technically called? Like bytes can have different lengths, and so the sizes can vary in some surprising ways. Yeah, we'll get to that. Okay, so we'll discuss this topic in detail in storing UTF-encoded text with strings in Chapter 8. Okay. Compound types. So all of that was just scalar values, things that were, roughly speaking, considered to be just a single value. But compound types are going to be multiple values together. So compound types can group multiple values into one type. Rust has two primitive compound types, tuples and arrays. Great. I think I like both for different reasons. So we'll get into that. The tuple type. A tuple is a general way of grouping together a number of values with a variety of types into one compound type. Tuples have a fixed length. Once declared, they cannot grow or shrink in size. And that, if I recall, is because they are stack allocated, where everything is kind of supposed to be immutable and fast on the stack, and the heap memory, you can change things a bit more. You have more control over the contents of the heap in a dynamic way, but it's slower. So we create a tuple by creating a comma-separated list of values inside parentheses. Each position in the tuple has a type, and the types of the different values in the tuple don't have to be the same. Oh yeah, right. Oh yeah, I should really think about arrays versus tuples versus, the thing I was thinking about is vectors. Okay, so we'll see again I need to remind myself about tuples versus arrays, but I think they're both... One of the main differences between tuples and arrays is that tuples can allow multiple types, whereas arrays cannot. Okay, let's get into this in review here. So each position in the tuple has a type, and the types of the different values in the tuple don't have to be the same. We got that. Okay, let's add another thing here. Cargo new the tuple type. So let's define a tuple. Call it tup or tup or whatever we're calling it. And here we need to be explicit about the types here, because it is not going to... Well, I guess there probably will just be defaults, I think. The usual defaults that we were just talking about with these different scalar values. But I think it's good to be explicit here. So the first thing is an I32. The second thing here, the second value for 6.4 is a float 64, and this value of 1 is a U8. Okay. So let's move on to the next thing here. Actually, I'm going to pause the video for a second, then we'll be right back. I'm just going to close the window because it's raining wildly. Okay, we're back. It's still pouring rain outside, but you know what? A little bit of rain is not going to stop us. So we've got this tuple. Let tup be of these types that we've specified, and then we've put these literal values. So let's see what else. Let's just do a quick cargo check on that. Mostly it's complaining about the usual thing that these tutorials haven't really talked about much, but just that we're not using these variables. That's fine. It's a valid tuple. The variable tup binds the entire tuple because a tuple is considered a single compound element. That's interesting. So to get the individual value out of a tuple, we can use pattern matching to destructure a tuple value like this. So this should also look somewhat familiar to Python programmers. Cargo new. And then let's just say, I don't know, tuple destructure, let's say. So here we've got let tup, and we're letting it infer types for us. Oh, interesting. Look at my editor here is trying to figure it out. I32. Interesting. Float 64. I did not know that it would do this. Or I just didn't notice. Anyway, okay, so let x, y, z be unpacked from tuple, and it's going to know what those types are. And then we can go print line macro. The value of y is, and we will just throw y directly in there and close the statement. And then let's go cargo run. And we got some warnings, but at the bottom here, we've got our printout of the value of y is 6.4. Very good. So, next example. The program first creates a tuple and binds to the variable tup. It then uses a pattern with let to take tup and turn it into three separate variables, x, y, and z. This is called destructuring because it breaks the single tuple into three parts. Finally, the program prints the value of y, which is 6.4. We can also access a tuple element directly by using a period, followed by the index of the value we want to access. For example, okay, here's an example. We've got the assignment of all the types, and then here we've used this .0 to access the first element, or the offset 0 in memory from the first element. And our 6.4 value is our x.1, the second value, or the offset from 1 from the beginning. And then our lat1 is equal to, or bound to, the value of x.2 for the third value, or the second offset from the beginning. All right, let's just type that one out real quick. Let's get out of, oh, I did a thing here. Let's move out of the character type. Oh, I'm still in there. Let's move out of the character type, the tuple type, up to here. There we go. Whoopsie daisy. Okay, so what should we call this? We should call this, honestly, let's just modify the tuple type example again. I don't see why not. Move. Let's also move that tuple destructure thing out of there. I've been recursively sticking these examples inside of each other, and that's not what I want. Okay. So we've got the beginning of this example here. Same numbers. Okay. Now we'll say let 500 be bound to the value of x.0, and then let 6.4 be bound to the value of whatever is in x.1, or the the first offset from the beginning. Let 1 be bound to the value x.2. Now, I think it has a different name. I see. That should take care of our naming problem. Let's do a little cargo check. Seems to be fine. Good. Next. The program creates the tuple x and then accesses each element of the tuple using their respective indices. As with most programming languages, the first index in a tuple is 0. Sure, 0 indexing, which is a fun little tidbit. Is like, it's the index you can kind of think of here as an offset from the beginning rather than a name for the position. It's just that happens to also be a corresponding thing. So anyway, it doesn't matter. The tuple without any values has a special name, unit. The value and its corresponding type are both written as an immediate open-close brackets and represent any empty value or empty return type. Expressions implicitly return the unit value if they don't return any other value. I am quite sure we'll come back to that, so I won't talk about it more, but yeah, it's the closest thing I can think of for Python. The way that behaves is like the none type. Okay, so the array type. Let's dive in. Another way to have a collection of multiple values is with an array. Unlike a tuple, every element of an array must have the same type. Unlike arrays in some other languages, arrays in Rust have a fixed length. We write the values in an array as a comma-separated list inside of square brackets. Let's do it. Let's go cargo new, the array type. Let A be bound to 1, 2, 3, 4, 5. There's some syntactic sugar here in Rust so that you don't have to do explicit sequences like 1, 2, 3, 4, 5, but that's okay. This is a good starting example. Go cargo. Cargo, check. Wonderful. Wonderful. Arrays are useful when you want your data allocated on the stack, the same as the other types we have seen so far. Okay, so the tuples were also on the stack, so nothing is heap allocated yet. We'll get there. Vectors especially are kind of the mutable heap version corresponding to both of these to some extent. Rather than the heap, we will discuss the stack and the heap more, rather than the heap, right? So in parentheses here, we will discuss the stack and the heap more in chapter 4. Or when you want to ensure you always have a fixed number of elements. Sure. So an array isn't as flexible as the vector type, though a vector is a similar collection type provided by the standard library that is allowed to grow or shrink in size. If you're unsure whether to use an array or a vector, chances are you should use a vector. Chapter 8 discusses vectors in more detail. You're definitely getting, as far as I know, in terms of program correctness, you're getting a wider variety of functionality out of a vector. But sometimes the right answer is to have some thing that is on the stack that you can't modify, truly can't modify. There's some advantages there. So, however, arrays are more useful when you know the number of elements will not need to change. For example, if you were using the names of the month in a program, you would probably use an array rather than a vector because you know it will always contain 12 elements. I guess in the comparison of the two, yes, that's true. Like if you have some canonical set of values that you want to have in your program and reuse that, kind of makes sense to use an array rather than a vector. But here you could also use enums if you wanted more bells and whistles attached, or if you wanted to do certain kinds of pattern matching with the switch statements. Maybe switch statements also work with these literals. We'll see. Okay, you write an array's type using square brackets with the type of each element, a semicolon, and then the number of elements in the array, like so. Right. So this is what I was saying before. Oh no, this won't generate it, but there is some notation to generate them concisely. So I32, and there's 5 elements. Okay, no problem. Oh, can we run this? No output. I guess that makes sense. There's no print line macro or anything like that. Here, I32 is the type of each element. After the semicolon, the number 5 indicates the array containing 5 elements. You can also initialize an array to contain the same value for each element by specifying the initial values followed by a semicolon and then the value of the array in square brackets as shown here. I wonder, I'd be curious to see some examples of where I would actually want to use this, where it's the same value and it's immutable. You know what I mean? Like I could see starting off with a constant vector and then changing the vector because the constant was just a placeholder for something. But then I think about, like, why would I want the exact same value? What does that get me over just storing like a literal integer on the stack and reusing that? I am curious about that. Okay. The array named A will contain 5 elements that will all be set to the value 3 initially. This is the same as writing let A be bound to the value of 3, 3, 3, 3, 3, but in a more concise way. Totally. Accessing array elements. So an array is a single chunk of memory of a known fixed size that can be allocated on the stack. Beautiful. I like these just very memory-oriented definitions of data structures. It's so refreshing over trying to understand things purely in terms of syntax. So you can access elements of an array using indices, indexing like this. Okay, so let's type that out, that example. So cargo new, we'll call this accessing array elements. And I misspelled accessing. Still looks wrong, but we'll go with it. Okay, let A be bound to the values of 1, 2, 3, 4, 5. Good. And then we'll grab some values. Let first. Now notice that with the tuple we used period, but here this looks a lot more like the indexing that we're familiar with for lists in Python. Let second be bound to the value of a at the offset of 1, index of 1. Cargo check. Good, good. In this example, named first, we will get the value 1, because that is the value at index 0 in the array. The variable named second will get the value 2 from the index 1 in the array. Sure. Sure. So, invalid array element access. Let's see how what happens if you try to access an element of an array that is past the end of the array. Ooh, yes, because in some languages, it will like let you do this and it'll break at runtime. I think Rust is going to stop us at compile time. So, say you run this code similarly to guessing game in chapter 2 to get an array index from the user. You got use. So here, by the way, we're getting this little Ferris thing. This code panics. We're expecting an error. Okay. Cargo new. And we're just going to type out this example as we go through it. Invalid element access. Let's see what we got here. So at the top, we're going to include, we're going to use standard IO, and we'll let A be bound to the values of 1, 2, 3, 4, 5, as before. And then print line macro. Please enter your password. Nope, array index. And then we'll let mute index. We're creating a mutable variable, remember. And we're just going to create a new empty string. And then go IO, standard in. And now we're going to write some chained out functions here. Read line. And we're going to pass in a mutable reference to index so that if something successfully gets read, it's going to go into that variable index. And we're going to expect failed to read line. And then we'll let index be bound to something of usize type, index. And here we're going to trim, just remove some white space, and we're going to parse. Remember that parse is looking over here to try to turn it into a usize. And then we'll go expect, and index entered was not a number. What we Pythonistas often call nans. Okay, so let element be bound to the value of A, offset by index, and print line macro, the value of the element. At index, and then we're going to put in the value index is element. Any errors? According to Ferris here, it's not supposed to compile. It should panic. Maybe the compiler's just fine with it, though. Like we're saying that this should error, so maybe the compiler isn't saying that anything is wrong. Let's go cargo check. Yeah. Cargo build. Cargo run. So now let's say I put in 1. The code compiles successfully. Just going to see what else they say here because I didn't really see an issue with any of that. If you run this code using cargo run and enter 0, 1, 2, 3, 4, the program will print out the corresponding value at the index of the array. Okay, that's what we are seeing. If you instead enter a number past the end of the array, such as 10, you'll see an output like this. Well, golly gosh darn, we got to do it. Let's put in 10. Thread main panicked at source main. Index out of bounds. The length is 5, but the index is 10. Run with Rust backtrace equals 1 environment variable to display backtrace. We should look at backtraces at some point, but not today. Okay, the program resulted in a runtime error at the point of using an invalid value in the indexing operation. The program exited with an error message and didn't execute the final print line macro statement. When you attempt to access an element using indexing, Rust will check that the index you've specified is less than the array length. If the index is greater than or equal to the length, Rust will panic. This check has to happen at runtime, especially in this case because the compiler can't possibly know what a value a user will enter when they run the code later. So that's actually a really important problem to think about with Rust, is that yes, it's got a bunch of guarantees on memory safety, but that doesn't mean that there aren't a wide variety of bugs that can occur. Some of them and issues and crashes because of things like user input, right? It should be sanitized, it should be checked to make sure that it is a correct type of input in the first place, that it's valid. And if not, you have to decide, should it? Like this program, if you're really just fine with running this as a little script and that it panics when it's out of bounds, then that's fine. But if you wanted to write a program where the user could try again with new input, you don't necessarily want the program to completely crash. Okay, so this is an example of Rust's memory safety principles in action. In many low-level languages, this kind of check is not done. And when you provide an incorrect index, invalid memory can be accessed. Rust protects you against this kind of error by immediately exiting instead of allowing the memory access and continuing. That's good to know. It actually prevents it. It's not reactively failing to it. It is actually preventing it. So Chapter 9 discusses more of Rust's error handling and how you can write readable, safe code that neither panics nor allows invalid memory access. Okay, so that was our first look at data types. These are just the really basic types in the Rust programming language that are going to be the bread and butter of a lot of the programs that we'll write in the Rust programming language. Hopefully that's interesting and useful to you. I will catch you in the next video. See ya.